So let's look at this one here. We want to find the derivative of f of x equal to sine cubed of x to the fifth plus e to the 3x. I would take the initial step of rewriting it as f of x equal to sine of x to the fifth plus e to the 3x all cubed. So this is a little easier to tell what's kind of the outermost functions, I like to call it. When we differentiate, finding f prime of x, we're taking the derivative of something cubed. We're going to get 3 times our something squared, and then we're going to multiply by the derivative of the inside something. So our inside something is sine of x to the fifth plus e to the 3x. And then we want to multiply by the derivative of that inside stuff. So we're multiplying by the derivative of sine of x to the fifth plus e to the 3x. I'm thinking of that as sine of some new stuff. I know the derivative of sine of x is cosine of x. So the derivative of sine of some new stuff is cosine of that new stuff. But then we said stuff again. So we now have to multiply by the derivative of this new stuff. So I have to multiply by the derivative of x to the fifth plus e to the 3x. The derivative of x to the fifth is 5x to the fourth. The derivative of e to the 3x is actually another chain rule problem. The derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff, which is e to the 3x times 3. Notice here that that 3 only gets multiplied by the e to the 3x, not by the 5x to the fourth. Kind of a little tricky there. Cool. Questions? Observations? All right, let's continue on. So really, I should just say everything from now on, the chain rules is always in play. Like if you're taking a derivative, you should be thinking, I'm taking the derivative using the chain rule, and maybe my inside function isn't that complicated. Maybe my inside function is super complicated. But every time you're taking a derivative, you're always thinking of leaving the inside stuff alone, and then at the end of the process, multiplying by the derivative of whatever the inside function was. So let's do a few examples of implicit differentiation. Yeah, so let's say we want to, for the following, find the, let's do equation. Let's find the equation of the line tangent to, what have I got here? Something kind of funky here. X cubed plus 4xy minus 3y squared plus 8y equal to 9x squared minus 7 at the point 2, 3. I will point out we have half the information we need, right? If we're trying to find the equation of a line, a tangent line, we need a point, which we have. The point is 2, 3, and we need a slope, which we're going to find. The way we find the slope of the tangent line is by taking a derivative. In this case, we're doing it implicitly, right? Well, I couldn't solve this equation for y if I wanted to. So we're just going to differentiate both sides, pretending like y is a function of x. So the derivative of x cubed is 3x squared. The derivative of 4xy, I'm going to have to use the product rule. I'm going to say, well, I've got a 4x, so the derivative of 4x is 4 times leave y alone, plus, then we switch it up, leave the 4x alone, and the derivative of y is y prime. Minus the derivative of 3 times y squared. Again, when I'm doing this, I'm thinking of y as some stuff, as a function of x. So 3 times some stuff squared, the derivative is 6 times my stuff to the first times the derivative of the stuff. Same kind of deal for 8y. The derivative of 8y is going to be 8 times the derivative of y, which is y prime. On the right-hand side, easy enough. The derivative of 9x squared is 18x, and the derivative of 7 is 0. And here is, so I would say that in my mind, there's kind of 2 varieties of implicit differentiation problems. This is the one where if you're trying to find the slope at a particular point, after you differentiate both sides, you immediately then plug in your x value and your y value. So we're going to plug in right now We're gonna plug in x equal to 2 and y equal to 3 to get, let's see here. So 3 times 2 squared is 3 times 4, so 12. Plus 4 times 3 is also 12. Plus 4 times 2 is 8 times y prime. Minus 6 times y is 6 times 3, so 18 y prime. Plus 8 times y prime equals 18 times 2, which is 36. Combine the y primes together, so I have 8 minus 18 is negative 10, plus 8 is negative 2. So I have a negative 2y prime equal to 36 minus 12 is 12. So it looks like y prime here is going to equal negative 6. What that means for me is that for this particular point on this graph, the slope is negative 6. For other points, it'd be other values, but we don't care. We're only been asked about this one point. So we have the slope, we have the point, and we can find the equation of the line. So we're going to get y minus 3 equals negative 6 times x minus 2. It's pretty standard to solve for y. So y minus 3 equals negative 6x plus 12. So y equals negative 6x plus 15. Do another example that's a little bit different flavor-wise. So let's read how this question reads differently. This one is going to say find y prime for the equation x cubed plus y to the fourth plus tangent of y equal to e to the y plus sine of x. And I would point out or notice that this question is saying find the derivative, not finding the slope at a particular point, but finding the derivative in general. So in this case, our derivative y prime is going to be a function of both x and y. We're going to solve for y prime with all the variables still left as in because we don't have a point to plug in where we're finding a particular slope. So same kind of work. We're going to take this equation, and the first step is going to be to just differentiate both sides of that equation. Again, pretending or assuming that y is a function of x. So I want you all to try your best to differentiate both sides here. So go ahead. There's your equation. Start taking some derivatives. Differentiate both sides. We should get the derivative of x cubed is 3x squared the derivative of some stuff to the fourth is 4 times my stuff cubed times the derivative of my stuff. The derivative of tangent of some stuff is secant squared of the stuff times the derivative of the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative sine of x is cosine of x. So whenever we have a y there, we're treating it like some stuff, and its derivative is going to be the derivative, but then at the end of the process, we have to multiply by the derivative of y. And most of the time people are totally cool with this. I feel like the one time people actually get thrown off is when you just have a y. It's like in the previous example, when we were differentiating 8y, we just got 8y prime, which makes sense, right? If you're taking the derivative of y, the derivative of y is literally the derivative of y. If you prefer, I don't, but if you prefer, you can think of the derivative of y as, oh, the derivative of y is 1, but then we have to multiply by y prime. I don't like that as much. I feel like it's really less the right answer, but it still works. Okay, after this first step, the rest is algebra. That doesn't mean it's easy, but you're done with the calculus part of this. Now we just have to figure out how to get all the y primes on one side and everything else on the other side. So I'm gonna bring all my y primes to the left, although it doesn't really matter which side you pick. I feel like we can do 2 steps at once here. I'm going to bring all my y primes to the left and also factor out a y prime. To factor out a y prime, I'm going to have a 4y cubed, a plus secant squared of y, and a minus e to the y. On the right-hand side, I'm going to have my cosine of x minus 3x squared. The last step is to divide both sides by whatever is multiplying by y prime. So we're going to get y prime equal to cosine of x minus 3x squared divided by 4y cubed plus secant squared of y minus e to the y. And then if they ask you, if they ask you like to find the slope of the tangent line at a particular point, you can plug in the point. Which again, you should just do that first if you can. But question?
So where did you ask the point? Put the x value
and the y value. You have to put x and y. So yeah, and so for example, let me think for a second here. 0, 0. No, that's not going to work out. Sure. No, I don't. Yeah, sure. So for example, if they said, what is the slope of the tangent line? That's a bad choice. I thought I had something that was going to work, but it's not going to work. Well, no, I don't love that at all. Here's the issue. It's hard to find the point that's actually on this graph, right? Because the only one I can think of is the point 0, 0, because if x is 0 and y is 0, you get 0 plus tangent of 0 is 0. Nope, that doesn't work either, because e to the 0 is 1 and sine of 0 is 0. Nope, it's not a good point. No, I don't really want to do that. So, but if you had a point that was on the graph, say for example, here's a point that I know isn't on the graph, but I'm just going to make it up. Let's say we had the point, I don't know, pi, 0. If that was a point that was on the graph, and you want to find the slope of the tangent line at that point, you would plug in pi for x and 0 for y, and then get whatever your value was, which would not be particularly nice here. That'd be the slope of the tangent line at that point.
points for the
That one more time?
intercept form.
Well, so I'm just talking about the slope of the tangent line. I think you're talking about finding the equation of the tangent line. Yeah. So yes, if we wanted to find the equation of the line tangent at this point, you'd find the slope, and then you would say y minus y1 equals the slope times x minus x1. Should we do one more? Yeah.
The equation, and it was like find like c y equals c square root of x.
Say more.
So they gave us the equation of the line.
Okay, the equation of the line.
That gives the equation of the
Okay.
line. Y equals c square root of x.
So we have f of x equal to c times the square root of x. And the equation of the line tangent was
Y equals 1/2 x plus
9/2.
Yeah.
y equals, say it one more time, 1/2 x times plus. Okay. And did they give you the point of tangent here? Interesting. Okay, sure. That's fair. All right. So if I want to find so here's the thing. I'm ignoring that 9/2. Yeah, this is all the information we have?
Said find C.
Okay. So here's what I know. I'm looking for, yeah, here's what I know. So I know that f prime of x is equal to c times 1/2 x to the negative 1/2. And I know that, yeah. That's a tricky, is this like a bonus question? Okay. Sorry, 1 second here. I have a guess, but I feel like I'm just assuming here. Right, we want this to equal 1/2. And we also know that, no, we also know that we want our y value. So we can say that, well, whatever x is, you should get the same y value here and here. Let's think about the picture for a second. This is essentially looking like this. Right? And I do know it goes to the origin because it's c comma root x. And then I'm looking for the equation of this tangent line right here. So I know the equation of this line is y equals 1/2 x plus 9/2. Right? I know at this point here, this point, let's say it's, I really want to use other letters here. Let's say this is the point. How tricky do I know? Let's say this point A comma B. I know two things. I feel like I'm introducing too many variables here. But let's do it anyway. So A comma B, I know that 1, the y value B should equal C times the square root of A. Because it has to be, right? It's on this graph here, y equals C root x. I also know that it satisfies this equation here. So that B equals 1/2 x, sorry, 1/2 A plus 9/2. So what I was trying to say, and kind of getting a long way, is that these two values have to equal each other for this value of x. So it's also true that C times the square root of A equals 1/2 times A plus 9/2. Or if you prefer, you can use x, right? You can say C times the square root of x equals 1/2 times x plus 9/2. That's going to allow us, I think, to, yeah, it's still a little tricky. This is a tricky problem. Yeah, I don't love this problem. Yeah, I really don't like this problem. Yeah.
What I did is I found a derivative of the y equals c times the square root of x.
Yep.
And I found with the algebra that the square root of x is equal to x. So then you plug it
So
in.
hold on. How are we getting that?
So you have 1/2, or the derivative of y equals c times the square root of x is equal to c divided by 2 square root x, right?
Sure. And that's equal to 1/2.
Yeah, because that's the slope we want.
Right.
So then we solve for c and you get square root of x.
Sure, I like that. So c equals the square root of x. Okay. But it's only equal to the square root of x at this one point. Okay.
And then I substituted y in the tangent line equation, or sorry, I substituted because the point of b is equal to c square root x, that's the input. You substitute it in for y in the tangent line, and you could also then substitute the c and then solve for x.
So we're saying that this b here is equal to our y value, which is equal to c square root of x, right?
Yep.
But then you're also saying, say it again.
So then when you write out the tangent equation,
Uh-huh.
you could substitute y for c square root x, and then you could substitute c again for square root x, so you get x.
Okay, that seems plausible. So I like that. So what we're saying here is in this equation, the y value should be that y value there. But the y value is, I see, we're plugging in points. Okay, so we can plug in the y value there, which is c root x equals 1/2 times x plus 9/2. And then you're saying at that particular point, it's also true that c is equal to the square root of x. Okay, I'll buy that. So root x times root x is x. X equals 1/2 x plus 9/2. So it looks like we're gonna get that x minus 1/2 x, which is 1/2 x, is equal to 9/2, which means x is equal to 9. If x is equal to 9, that means c is equal to 3. So what we're saying here is that our function is 3 root x. And the point of tangent c is 9, 9. Gross. It feels very unintuitive. Yeah, I don't like this problem. So yeah, that's I don't know if there's a better way to do it. I don't really see a better way to do it. Yeah. And then I'll let me see one thing for a second. So that's 3. Nope, yeah, that totally works. Okay, that'll give you a simple 1/2. Yeah. Yeah, that works. But it's not fun. All right. Other questions about this? Other questions from the exam or on the topic of the exam? It's never really fun to talk about the exam right after you've taken it because you're like, well, I kind of remember how I did it, or I exactly remember how I did it, but I haven't gotten a grade on it yet. So it's like, I just get to either feel like I did great or feel like I didn't do it well. So I'm happy to talk about exam questions, but also we should move forward because I'm going to move forward, but I'm always happy to go back. Let's talk about related rates, which I feel like doesn't get given a lot of time in this particular textbook. Like related rates is like a section of a chapter, which in other textbooks, it's like a whole section to its own. So we'll talk about related rates for a little bit. Again, as the name suggests, they are related rates, meaning you're given one rate, you're asked to find a related rate. Was there a question? Yeah. Okay, I'll hold off on the related rates for a moment. Okay, sure. Say more. So P times E to the negative Q. DADP. Okay, to me this doesn't read as a related rates problem. Well, are we given any rates? Did they tell us how anything is changing? Did they tell us like that the rate of change of A is 5 meters per second or right? So to me, if they're not giving you a rate of change in words, it's really typically not a related rates problem. To me, this reads as an implicit differentiation problem, which again are not that far off from each other, right? They definitely have a lot of things in common, but I would say this is still an implicit problem. No, it's okay. I don't mind at all. I just want to make sure you all are aware of like what the problem's going to asking. So they're asking us to find what was it, DADP or DPDA? Cool. From which section? I make sure I'm seeing it all right. Okay, so that's a row e to the negative QA equal 1 minus A. So we're finding, yeah. So when you look at this, you're thinking of A as being like your Y and rho or P as being like your X. So really A is some function of rho. So when we differentiate this, A is our quote unquote stuff. So if I'm going to differentiate rho times e to the negative QA, I'm going to have to use the product rule because I have a function, or I have a function of my independent variable rho and another function of my independent variable A depends on rho. So I differentiate this side, product rule. This is my F, this is my G. My F prime, well, the derivative of rho is just 1, right? It's just the regular, it's like our X. So our F prime is going to be 1. We're going to leave G alone for a minute and get e to the negative QA plus, then we switch it up, we leave rho alone. And then we multiply by the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of a constant, negative q, times our function is going to be negative q times the derivative of our function. So here is our g prime. And again, right, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of negative q times a is negative q times the derivative of a. On the right-hand side, derivative of 1 is 0, derivative of negative a is negative derivative of a. Just like any implicit differentiation problem, after the first step, the rest is algebra. I'm not saying that to say it's easy, just that it's just algebra after that, meaning it is processes we are familiar with, kind of. So I'm collecting my a terms on my derivative of a terms on one side. So I'm gonna bring all this over to the other side, leave this over here. So I have e to the negative qa equal to, that minus sign is going to turn this whole thing positive over here. So it's going to be positive rho times e to the negative qa times q times dAd rho minus dAd rho. Factor out the derivative you're trying to solve for. So if e to the negative qa equal to dAd rho multiply by rho e to the negative qa times q minus 1. Finally, divide by this to get e to the negative qa divided by rho e to the negative qa times q minus 1 equal to your derivative. That's what that looks like. Not terrible, but definitely made harder by using kind of atypical variables. Right? If this had instead been x times e to the negative q y equal to 1 minus y, it might have been a little easier to find dy dx. Oh, I'm sorry, I didn't say that. Different answer? That's the same. Yep. What they're doing there is they're multiplying the top and bottom by e to the qa. So you multiply the top by e to the qa, you're going to get 1. Multiply the bottom by e to the qa, you're going to get rho times q minus e to the qa, which should be the same thing, right? Yeah. Yeah, sometimes the answer that you get or I get and don't feel like doing anything more with is the same as what they've got, just not simplified the same way. All right. So let's move on. As fun as it is to talk and commiserate about the test, be like, oh, well, I didn't do that one 100% right. Let's talk about some related rates here. So I do feel like most of the related rates examples in your textbook are kind of biology related, and not that we won't look at one of those or maybe two of them. Most of your math teachers have examples in their heads that are not like that. So even though the book questions are kind of biology related, people often like to ask ones that are kind of more physical shape related, because that's some, like, Fidel has spent probably the last 50 years asking questions related rates wise that were like, this, this dimension of the shape is changing this way. How is the volume of the shape changing? Right? That's just so ingrained in my brain and probably his brain that you're probably going to see a question like that in the future. So here's a couple examples of that, and then we'll do one biology one that's a little less like that. I don't love that one, though. Let's do this one. Yeah. So here's the following question. We have, and these are always pretty wordy. So the radius of a cylinder is increasing at 3 feet per hour, while the height is decreasing at a rate of 2 feet per hour. How fast is the volume changing when the radius is 5 feet and the height is 4 feet. And I will just point out here that almost any related rates problem typically has to tell you something is changing at some rate, ask you how something else is changing, and say at a particular moment in the process, right? Oftentimes people, when they're not really thinking carefully, will forget to say when the whatever is whatever, and then you're like, well, I don't know what to plug in there. Sure, let me read it again. The radius of a cylinder is increasing at 3 feet per hour, while the height is decreasing at 2 feet per hour. How fast is the volume changing when the radius is 5 feet and the height is 4 feet? And yes, I know my writing is terrible. I am a little ashamed, but not so ashamed that you shouldn't ask. Like, definitely ask for good clarification. I know things don't always look great. So typically, if I am doing a related rates problem, I'm usually going to start off just by drawing a picture. There's my shape. And it's good to label the things that are changing. There's the radius. There's the height. And the first thing I want to write down is just what's changing. So I know that the radius is changing. So dr dt, the rate of change of the radius, is 3 feet per hour. And the height is also changing. The rate of change of the height is, well, the height is decreasing. So we should say that dh dt is equal to -2 feet per hour. All right, I should do one of those two. I like that problem. And then we want to know how the volume is changing. So typically, once we've written down all the rates that we know are changing and the ones that we want to know how they're changing, we then try to find an equation relating those variables. I should say relating those non-time variables. It's usually the equation for the area or the volume or the Pythagorean theorem or some surface area kind of like some sort of geometry equation. Here, the equation is going to be that the volume of a cylinder is pi times the radius squared times the height, or the area of the base circle times the height of that shape. Then we differentiate both sides. So right after you find the equation, assuming that you've got the variables you want, you're going to find the derivative or differentiate both sides. And this is where we're essentially doing implicit differentiation on both sides. So the derivative of v is going to be dv dt, or v prime if you like that notation. Although almost exclusively we use this Leibniz notation for related rates problems. We almost never use like the prime notation. It's just the way we do it. On the right-hand side, I'm going to have to use the product rule. So actually, let's just say that the constant pi hangs out. And we're going to do the derivative of r squared times h. Well, the derivative of some stuff squared is 2 times my stuff to the first power times the derivative of my stuff. And then leave the h alone. And then switch it up. Now I'm going to leave the r squared alone. And the derivative of h is just the derivative of h, which is dh dt. Cool. After this stage, we plug in. And we should either be told all the values that we need to plug in except for the one we're trying to solve for, or be able to find them. In this case, I think we're told everything. We're told what the radius is, what the rate of change of the radius is, what the height is, what the radius is, what the rate of change of the height is. So I think we can just plug in for everything here and figure out that dv dt is equal to pi times 2 times r, which is 5 feet, times dr dt, which is 3 feet per hour, times the height, which is, where'd you go? The height is 4 feet, plus the radius squared, which is 5 squared, times the rate of change of the height, which is -2 feet per hour. So simplifying this, we're going to get pi times, let's see, 2 times 5 is 10, times 12 is 120, and then that's 120, and that's 25 times -2, so -50. So let's say we're getting pi times 70 or 70 pi. And then at the end, I do think we should include the units. The units are going to be, well, so here's the thing. You shouldn't have to like look at the, like we can look at this and see that we have feet, right? Feet, yeah, times feet per hour times feet. So I should have feet times feet times feet, so feet cubed per hour or feet cubed per unit of time. But we should also just be able to say, we know it's how a volume is changing. A volume is measured in units cubed, whether it's feet cubed or meters cubed or inches cubed or whatever your unit of length is per unit of time. So we can just jump straight to the chase at the end here and say this should be measured in feet cubed per hour. Cool. So it's increasing, right? The volume is getting larger because our rate of change is positive. Even though this thing is getting shorter, it's getting wider much faster than it's getting shorter to account for that. So we're overcoming that. At least this moment in time. Later on, it might be a different story. Let's do one more, one more geometric one because there's definitely, yeah, there's a common thing that comes up. And then we'll do one biological one, and then we will talk about logarithms, logarithmic differentiation. Oh, sorry, not this. Sorry, exponential growth decay. That's next on the docket here. Yeah. Okay, let's look at this one. I'll try to write this a little bit more legibly. A water tank in the shape of an inverted cone, meaning point down, like an ice cream cone, with a radius of 4 feet and height of 12 feet, is being filled at 5 cubic feet per second with water. When the depth of the water in the tank is 6 feet, how fast is the water level rising? Definitely going to start off drawing a picture. So here's my conical tank. And the radius of this tank is 4 feet. And the height of this tank is 12 feet. And the water level is rising. So there's water in the tank. And whatever the depth or the height, whatever you want to call it, of the water is, we're going to give that a variable name because it's changing. Right? So things that are changing should get names of variables. You can call it H or Y, whatever you like. I'm going to pick H because that's pretty standard. So let's write down the things we know are changing. So in this, well, the things we know, things we're told. Let's see, a water tank in the shape of an inverted cone with a radius 4 feet, height of 12 feet is being filled at 5 cubic feet per second. So we are told, as far as our rates of change go, that the rate of change of the volume, so dV dt, is equal to 5 cubic feet per second. It's a lot of water. Maybe it's not a very good number. Oh well. And then we are being asked to find how fast the depth of the tank or the depth of the water in the tank is increasing. They said changing, but right, we know it's getting bigger because we're filling it up. Or they said rising, I guess. So we want to know what dH dt is. And I guess I could have labeled, although I wasn't really thinking about it, the fact that this little cone of water here also has another thing that's changing. Its radius is also changing. right? As the water level is higher, get a bigger circle at the top, it's got a bigger radius. So great, we've got the thing we're told how it's changing, the volume, and the thing we want to know how it's changing, the height of the water. And now we need an equation relating those two things. And I wish we had an equation relating just those two things, but we don't. In this situation, the equation we're looking for is the volume of the cone of water, and the volume of a cone is equal to 1/3 times pi times the radius squared times the height. And I don't love the fact that I have an R in there because they didn't tell me how the radius is changing. And while I could figure it out, that's not really what I want to do. So in this situation where you have more variables than you want in your equation, we have to do a little bit of work before we start differentiating. We're going to eliminate the radius variable here because we don't want it. It's actually relatively straightforward to do. We're just going to take this picture here, this cone, and find R in terms of the height. Here's the easy way to do it. What's the radius of the big cone? What's the height of the big cone? What fraction of the height is the radius? A third. Perfect. The radius is 1/3 the height. Totally works every time. Now, if you want to be a little bit more kind of, I don't know, if you want to write down more things, you could use the fact that we have some similar triangles here. And that in the big triangle, this length is 4 and this length is 12. In the small triangle, this length is R and this length is H. And you could say that H over R is equal to 12 over 4. And you could solve for R. H equals 3R. R equals H over 3. Still get the same place. Sorry, I think I see that. So typically for these cone ones, if you can tell yourself, oh, the radius is 1/3 the height, and you can see that, you're good to go. There's no more exploration that needs to be done. It is not wrong to say that because the ratio of the height to the radius in the cone is always the same no matter where you are. So then we're going to rewrite this as volume equals 1/3 pi times 1/3 h squared times h. And then we're going to make our lives easier and simplify this before we try to differentiate. That's going to be 1/3 pi times 1/9 h squared times h, which simplifies to 1/27 times pi times h cubed. That's our volume. Now we're ready to differentiate both sides. Definitely out of room, so I'll use another piece of paper. So differentiating with respect to time, we're going to get that volume equals 1/27 pi times h cubed is going to become dv dt equal to 1/27 times pi times the derivative of some stuff cubed is 3 times our stuff squared times the derivative of our stuff. I am always thinking about the chain rule. It's never going to go away. It's always there with you until the day you die. So anyway, now we should just plug in. I guess we could simplify a little bit if we wanted to. You could simplify this as dv dt equals pi over 9 times h squared times dh dt. Because 3 over 27 reduces to 1/9. 1/9 times pi is pi over 9. Now plug in. So we know, sorry, I know it's way up there, apologies. We know that dv dt is equal to 5, and we're trying to solve for dh dt. And we're also told that the height of the water, or the depth of the water, is 6 feet. So we're going to say that 5 for dv dt is equal to pi over 9 times 6 feet squared times the thing we're trying to solve for. I would probably simplify the right-hand side before I solve for dh dt. So 6 squared is 36. 36 divided by 9 is 4. So 5 is equal to 4 pi times dh dt. So it looks like dh dt is equal to 5 divided by 4 pi. What are my units here? Well, I was measuring the rate of change of volume in cubic feet per second. So the rate of change of the height should just be in feet per second. So dH dt is equal to 5 over 4 pi feet per second. So every one of these related rates problems is different, but they all follow the same kind of 4 or 5 steps. Figure out what's changing, find an equation relating those things, differentiate both sides, plug in what you know, solve for what you want. Kind of always the same 4 steps, maybe 5 steps. All right, let's do one more that is not the same as these other ones. I mean, none of them are the same, but it's a little bit different here as far as the setup. So here is the following problem. Yeah. So Boyle's law states that, I'm just going to read this. When a sample of gas is compressed at a constant temperature, the pressure and volume are related by the equation PV equal to C, where C is a constant. Suppose that at a certain instant, suppose that at some moment, the pressure is 150 kilopascals. And the volume is 600 cubic centimeters. Also, the volume is decreasing at 10 cubic centimeters per minute. How is the pressure changing? Or how fast is the pressure changing? So before we do any of this, let's do a common sense check here. Pressure times volume should be constant, according to this equation. So if the volume is decreasing, we should expect the pressure to be increasing or decreasing. Should be increasing, right? If that volume is getting smaller, the pressure is going to have to be getting larger so that their product still is the same constant value. Right? If two things multiply to a number that doesn't change, if one of them gets bigger, the other one has to get smaller and vice versa. All right. So here's what we know. I don't have a picture to draw here. So I know that I'm given that the rate of change of volume, dV dt, is negative 10 cubic centimeters per minute. That's the only rate of change I'm told. I'm asked to find how the pressure is changing. So I want to know what dP dt is. And unlike the previous problems, they've already given us the equation relating pressure and volume. So we don't have to go search for some geometrical idea of like a volume of a cone or something. We know that pressure times volume equals a constant. So 2, our equation already is pressure times volume equals a constant. And I think you have a choice here. You could solve for one of them in terms of the other one, or not. You can just differentiate both sides of this without solving anything. So let's actually look at both ways, just so you can kind of see it works out the same way either way. So you can either do this and say, great, I'm going to differentiate both sides. I'm going to use the product rule on the left. I'm going to take the derivative of P, so dP dt, times the volume, plus you switch it up, P times dV dt should equal the derivative of C. Or, since we know we're trying to find dP dt, we could solve this equation for P. Say that P is equal to a constant divided by V or multiplied by V to the negative 1, and then differentiate both sides and say that dP dt is equal to C times the derivative of something to the negative first is negative 1 times that something to the negative 2 times the derivative of that something. Seems very different. I'm curious if we're gonna end up with the same thing or not. Let's find out. So here I'm trying to solve for dp dt. I'm gonna plug in everything I know. So I know that the volume was told to be 600 centimeters cubed. So I have dp dt times 600. Plus the pressure was said to be 150 kilopascals. And then dv dt is -10. So let's see, solving for dp dt, I'm going to get dp dt equal to, so adding this over here, I'm going to get positive 1500. And then dividing by the coefficient of dp dt, I'm going to get divided by 600, which is going to simplify to 15 over 6, which simplifies to 5 over 2, or 2.5. And that should be measured in kilopascals per whatever my unit of time was. Why isn't it negative? Good question. So it's not negative here because I will point out that this here is a negative 1500. And so when I added it over to the other side, it was positive 1500. But I want to point out, this is why it was really good that we did the common sense check before, right? Over here, when we looked at this in the beginning, we said, oh yeah, if pressure times volume is a constant, and where'd you go here? And the volume is decreasing, the pressure has to be getting larger to compensate for that. So we were expecting dp dt to be positive, and we are glad that our expectations are being met here. Let's see if it works out the same way over here. So in this case, if I start, well, that C there is bothersome. I don't love that. What's going on with that, James? Yeah. Oh, yeah. Gotta be smart. Okay. So the constant, well, pressure times volume is a constant, right? So really that constant there is whatever the given pressure of 150 times the given volume of 600 is. That's what we're going to have for the constant there. Because P times G equals a constant. If you know the pressure at one time and the volume at one time or something, then that constant can never change. So automatically, I feel like doing it this way is less good. I had to think too hard to do it this way. Oh well. So I have 150 times 600 times -1. Instead of multiplying by v to the -2, let's divide by v squared. And volume is, again, 600. So I'm dividing by 600 squared. And then multiplying by dv dt, which is -10. And yeah, let's say things are going to work out the same, because I'm getting one of those 600s canceling. And then I have 150 times -1 times -10 is positive 1500 divided by 600, which is the same as what I had over here. So yeah, it works out the same. Requires a little bit more thinking. You still get 5 over 2, or 2.5. Interesting. I would say that for related rates problems, I am generally of the opinion that it's not in our interest to simplify this before we differentiate. I think taking this equation and just taking the derivative straight away using implicit differentiation is usually the better route to go. Yeah, it's kind of, that's it. All right. Think that's enough related rates for now. Let's move on to exponential growth and decay. Also a reminder, not that we meet on Mondays, but there is no class next Monday on the 11th, and it's Veterans Day. Don't come to UC Davis that day. We won't be here. So no class next Monday. It's a 3-day weekend, Friday or Saturday, Sunday, Monday. We will meet on Tuesday as usual, though. So I'll see you all on the 12th. So let's see, exponential growth and decay. So, oh, sorry, you can't see that. Let me zoom out just a tiny bit here. So you've probably in your mathematical career seen the formula for exponential growth. So the exponential growth / decay model, as we typically refer to it, is usually written something like y or y of t equal to c e to the ket. Where typically c is the initial population size or initial amount of stuff, how much you have at time 0, and k is usually called the growth rate or the, excuse me, or the decay rate. So k is the growth rate / decay rate. Actually, I'm missing a word that's really important. It's the relative growth rate or decay rate. And that is actually super duper important. Here's what you really should know about this moving forward, because I imagine most of you are planning on taking 17B and 17C. At least 17B for sure, probably also 17C. This is probably one of the most important equations that's going to come up in your future classes, because it's an example of a solution to a very important differential equation. So if we take the derivative of y, dy dt here, the derivative of c e to the kt, or the derivative of c times e to the stuff, is c times e to the stuff times the derivative of the stuff. And the derivative of a constant times t is the constant times 1. And what I want you really all to see is that, well, c e to the kt here is just y, or y of t. What we really have here is that dy dt is equal to y times k, or it's usually written as k times y. So what we are actually seeing here is that y equal to c e to the kt, the model for exponential growth or decay, is a solution to the differential equation dy dt equals k times y. Or in other words, if the rate of change of the population y is proportional to y, then you end up with a model for growth that is exponential growth. Let me say more about this. So what we're really saying here, if you're saying, and let's talk about growth specifically, because I feel like it's easier to kind of visualize. What this is saying is your population is growing at a rate that is proportional to how many people you have, if k is positive. And so if so basically, if you have 1,000 people, your population is going to grow at some rate proportional to that. But then it's going to grow, and then it's going to start growing at a rate proportional to the new population size. And every time the population grows, the rate of growth is going to be proportional to that new larger population, which is exactly the situation which is going to lead to exponential growth, because as your population is getting bigger, your rate of growth is also getting bigger. I will also say that means your relative growth rate. So growth rate and relative growth rate are different things. Let me give you an example. What if I said the population was growing at 1,000 people per year? Is that meaningful? No. Where am I talking about? Are we in Davis? Pretty meaningful. Are we in New York City? Not meaningful at all, right? So the relative growth rate, not growing at 1,000 people per year, but growing at 1,000 people per year per 60,000 people, or 1,000 people per year per 6 million people, right? One of those is much more significant than the other. So let me write that down just so we can all see it here. So a growth rate of 1,000 people per year isn't very meaningful. It's not telling you the whole story. Isn't meaningful, or really a better word here is isn't useful, to be perfectly honest. On the other hand, a relative growth rate, meaning the growth rate per the population size of 1,000 people per year per the total population, let's say it's Davis, of 60,000 people, that is a much more meaningful number. It's telling you, oh yeah, every year we're growing 1,000 people per the 60,000 people we have already. So just to kind of say even more about this, relative growth rate is going to be, well, the relative growth rate is exactly, check this out, the rate of growth, aka the rate of change, divided by the population size. And here's kind of the sum up here, is that for exponential growth, the relative growth rate is always constant. If you look back here, right, we saw that exponential growth is a solution to this differential equation. If you take this differential equation and divide both sides by y, you get that dy dt, the rate of change of y, divided by y, the population size, is equal to the constant k. So that's the whole kind of deal, is that when someone says words like the rate of growth is proportional to the population size, that immediately should clue you in that they're talking about exponential growth or decay. So whenever the rate of growth is proportional to population size, that means we're talking about exponential growth. And so words that mean the same thing. Phrase, so let's say we have some equivalent phrases here. I can think of 3 of them. Phrase 1, population is growing exponentially. Phrase 2, the rate of growth is proportional to the population size. Phrase 3, the relative growth rate is constant. All 3 of these phrases mean exactly the same thing. So when you hear any one of them, you should think, okay, we're talking about exponential growth. Every time I say growth, you should be hearing or decay, right? Because the growth or decay, it's really the same thing. It's just in one of those cases, the k value you find ends up being positive. In the other case, the k value you find ends up being negative. But they're really the same idea in general. All right, so let's see here. Let's actually do some examples now with the last 16 minutes we have here. Sure. Yeah, let's look at this example. So even though we said all that about growth rate and relative growth rate, the actual kind of execution of most of these problems doesn't really involve much in the way of derivatives or calculus. It's mostly algebra and pre-calculus skills. So let's take a look at some examples. I feel like I might have done this one. No, I don't think I did. So here is the following example. A bacterial culture, bacterial, I don't know. I'm not a biologist. A bacteria culture initially contains 700 cells. And okay, here we go. Grows at a rate proportional to its size. After 2 hours, the population of bacteria, or the number of bacteria, is 1,000. This first question I don't usually ask, but I'm going to ask it here. Find the population of bacteria. I feel like population is the wrong word to use here, whatever. Population size after T hours. This question really is just the first part of any kind of question. So really, here's what I would actually ask. I would actually ask, how many bacterial cells are there after 7 hours? Or how long does it take until there are 2,000 cells? And then before you did either of those things, you'd have to do this, which is another way of phrasing, find the model for growth. Meaning, we know it's going to be an exponential growth model because we use the magic words the population grows at a rate proportional to its size. That just means we have the usual exponential growth model. Y of t equals c e to the kt. And then before we can answer anything with actual numbers, we first have to find our c value and our k value so that we can then answer any other questions. We already know what c is. How many hundred is c? 700, right? C is always the amount you're starting off with. Now, even though we know that, I still like to make a little table over here. I'm a big fan of making a table with your times and your amounts. I know at the beginning it was just times 0. I have 700 cells. I know that 2 hours later I have 1,000 cells. So you could go straight to saying, great, we know that y of t is going to be 700 e to the kt. Or if you prefer, you can plug in 700 for y and 0 for t and solve for c and get 700. But then the next step, you actually do have to do, I think, a little bit more work. So here, now we're going to go ahead and plug into our updated model that y is 1,000. It's equal to 700 times e to the k times, and t is 2. And that will allow us to solve for k. So we're going to divide both sides by whatever coefficient you have here. So we're going to have 10 over 7 equal to e to the 2k. Take the natural log of both sides. The natural log of 10/7 equals the natural log of e to the 2k is just 2k. And finally, 1/2 natural log of 10/7 is equal to k. So there's our relative growth rate. Some number. Some positive number, by the way, I will point out, because the natural log of 10/7 is certainly positive. So here's our updated, fully fledged model. Our answer to this question is going to be y of t equals 700 e to the 1/2 natural log of 10/7 times t. And that is the population size after t hours, or population as a function of time. Okay, but then we like to ask other questions like how many bacteria after 6 hours? Well, the easy way to answer this question is by plugging in t equal to 6. So we know that y of 6 should equal 700 e to the 1/2 natural log of 10/7 times 6. And then if you really want to, you'd probably need to get a calculator to actually make this kind of worthwhile. I could say more about this, but it's not super important. Sure. Oh. Sorry, I don't really want to get up. I probably should. If you plug this into a calculator, you should be getting, sure. Oh my gosh. 700 times all that is going to be approximately 2,041. There is something worth noting here. And that's the following. I picked an amount of time that was exactly an integer multiple of the interval we were given. And this is something I think is worthwhile. For exponential growth or decay, if the amount of time that has elapsed is a constant, the multiplication factor is the same constant. So I know that in 2 hours, I multiply by how much? It's not a great number. I multiply by 10 over 7. So every 2-hour interval, I should multiply by the same amount. So in another 2 hours, I should multiply by another 10/7. So I'm going to get 1,000 times 10 over 7, which is 10,000 over 7. And then in another 2 hours, getting me to 6 hours, I should multiply by another 10/7, which is going to get me to 100,000 over 49. And if you use a calculator to calculate that, 100,000 divided by 49 is the exact same number. So I do think it's good to know that for exponential growth and exponential decay, it's not a linear relationship where every amount of time you increase or decrease the amount by the same amount. It's a exponential relationship where every constant amount of time you multiply by the same amount, whether it's getting larger or getting smaller. Exactly like a half-life. A half-life is a measurement of an amount of time, the amount of time it takes to multiply by 1/2. That amount of time is constant, and every time that amount of time elapses, the amount of stuff you have is cut in half, multiplied by 1/2. So this is the less interesting question to answer. The more interesting or harder question to answer is how long until you get to some amount. For example, how much time until there are, say, 3,000 bacteria. Then you do the same sort of thing, except instead of plugging in t equal to 6, you would plug in 3,000 for y. Say that 3,000 equals 700 times e to the 1/2 natural log of 10/7 times t. And then it's the same sort of process as solving for k before. We're going to divide both sides by 700. You're going to get 30 over 7 equals e to the 1/2 natural log of 10/7 over times t. Take the natural log of both sides. You get the natural log of 30 over 7 equal to the natural log of e to all that is just the all that, the 1/2 natural log of 10/7 times t. And then multiply both sides by 2. You get 2 natural log of 30 over 7. Divide both sides by natural log of 10/7. And that's going to be your answer. And then you could pull out a calculator and get a decimal approximation. I guess we could do that. Not the worst thing in the world. Let's see what we get. 2 times the natural log of 30 divided by 7, divided by the natural log of 10 divided by 7. So before I put enter here, let's think about what our answer should be. I know it took 6 hours to get to 2041. So it should definitely be more than 6 hours. Oh, good. It's 8 hours. That seems about right. Approximately 8.16 hours. And if you multiply by another 10/7, right? So I should say, back up here for just 1 second. Another 2 hours would get me to 8 hours. If you multiply this amount by 10/7, 100,000 times 10, oh my gosh, it's 1,000,000. Is that enough zeros? No, that's enough zeros. Divided by 49 times 7, which is 343. Bless you. So after another 2 hours, you get to 2,915. So yeah, seems pretty reasonable that it should take a little more than 8 hours to get to 3,000 bacteria. Cool. Oh yeah, that's a good question. Okay, here is actually a good question that is kind of calculus-y. In part C, what's the rate of growth after 3 hours? Actually, let's be smarter about this, James. Let's make it 6 hours, a number that we've already used. Okay, so this is where you don't want to do more work than you have to. So I will point out that we know that all this came from the differential equation dy dt equals k times y. Or in other words, the rate of change of y equals the constant k times how big the population is. Well, we know both of these things at this particular moment. If we're trying to find the rate of change of y when time is equal to 6, it's going to equal the k value that we found already times y of 6, which we already found in part B. So it's going to equal k, which is our 1/2 natural log of 10/7 times our y of 6, which is this terrible number here, 700 e to the 1/2 natural log of 10/7 times 6. I know it's kind of awful. I won't lie. It's actually more than kind of awful. It's pretty awful there. But I feel like this is less work than actually taking the derivative. So I'll say the other way we could have done this was by saying, well, great. My y of t was 700 e to the 1/2 natural log of 10/7 times t. And then you can take the derivative and get 700 e to the stuff times the derivative of that stuff, which is going to be exactly 1/2 natural log of 10/7. And oh, look, it's the exact same formula. I just have to plug in 6 here to get the same thing I have here. So this actually, well, I feel like this is more of a web work kind of question, which I know Adele isn't doing web work. So this kind of question comes up more in web work, where they're like, oh yeah, find the rate of change. And really they want you to just like take the value you had and multiply it by k instead of taking the whole derivative and plugging it in. Either way works just fine though. All right, let's see. Can I say more in 4 minutes? I mean, I sure could. Should I say more in 4 minutes? Yeah. .6, maybe. Let's take a look at it. I was just about to do a Newton's law of cooling question. I can do one. I'm gonna do one similar just because I have one already set to go. So let's look at a similar problem. Well, actually, we'll look at this one. We'll talk about the setup here. So in a murder investigation, the temperature of the corpse was, so let's write down the pertinent information. So we know that the temperature of the corpse was 32.5 degrees centigrade or Celsius. I don't know, whatever that C means. 32.5 degrees at 1:30 p.m. and 30.3 degrees, so it's cooling 1 hour later at 2:30 p.m. The surrounding temperature, which we typically call TS, was 20 degrees centigrade, Celsius. I don't know. Aren't those the same? Probably. What time did the murder happen? Great. So I'm going to call whatever the initial time of observation is, time equal to 0. That's usually your best bet. Let's call this time equals 0. And this is going to be time equals 1. I think we're given Newton's law of cooling in the textbook. Let's go back and take a look real quick. Yes, we are. It's right there somewhere. Are we giving? Okay, sure. They give it to us that way. That's fine. Yeah. So they don't actually give you the nice formula, which is totally okay. So here's Newton's law of cooling. And the general idea of Newton's law of cooling is that the rate of change of the temperature is proportional to the difference between the temperature of the object and the temperature of the surrounding whatever, refrigerator, air, etc. Oh, look, we have a rate of change being proportional to the original function, essentially. That's also a model for exponential growth or decay. So we could say here that, and I have to remember how this works exactly. Yeah, so we have, yeah, let's just do it the smart way. Fine, sure. I don't love the way they set this up personally, but fine. That the temperature itself is going to equal, sorry, it's always been, this one's always like, how do you do this again? Sure. The rate of change of temperature is equal to K times T minus TS. I don't love this whole change of variable thing they do. So here's what I'm just going to say. I know that T minus surrounding temperature should equal CE to the K times T. Let's think about that for a second. If we took the derivative of both sides, yeah. So I take the derivative of this side. The derivative of this would be dt dt. And the derivative of the surrounding temperature, which is a constant, should be 0. On the right-hand side, the derivative of CE to the KT is going to equal CE to the KT times the derivative of KT, which is K. But look, that's exactly CE to the KT, which is T minus TS times K. Sorry, that looks terrible. So we're exactly getting the differential equation that we started with to set off this whole process. So it is true, and I would kind of recommend, I don't know, knowing this, is if you're solving a Newton's law of cooling problem, you're always gonna get that the difference in your temperature of your object and the surrounding temperature is equal to C e to the K times T. And there's more to this formula than that, but I feel like that's all you really need to know. So in other words, the temperature at any time T is equal to the surrounding temperature plus C e to the KT. Now it's our job to find C and K.
I just want to say, I learned the temperature as T, so the temperature of the surrounding plus, and then in the quantity, the initial minus the surrounding.
Right, which is about which is exactly where we're about to get to. And so I know it is 11:52. If you need to go, that's totally fine. We'll wrap this up real quick here. So I'll just point out that if you plug in time equal to 0, you're going to get TS plus CE to the 0. So your initial temperature at time 0 is equal to TS plus that constant. So exactly what he was saying there, the constant is going to be the initial temperature minus the surrounding temperature. So then we have that really our equation is the temperature at time T is TS plus T naught minus TS times e to the KT. And then we can find K in the usual way by plugging in a later data point. So here's what our setup looks like. It's that the temperature at time T is equal to the surrounding temperature, 20 degrees, plus our initial temperature, 32.5, minus the surrounding, 20, so 12.5, e to the KT. Here's how we finish this off. I'm not actually going to finish it off. I'm going to tell you what to do. So the next step is going to be plug in temperature equal to 30.3, time equal to 1, and solve for K. And then after you do that, we want to know how long it took for the body to get here. So we have to ask ourselves, what's the temperature of the body when the person dies? Like, and do they even say this in the problem?
Yeah, it's at 37.
Oh, okay, good. I was like, I know it's something close to 37. Oh, yeah. So what you're going to do after this is then you'll have the temperature at time T equal to 20 plus 12.5 e to the KT, and you'll plug in this value for K, and then set this equal to 37 and solve for T. Now here's what's going to happen. When you solve for T, T is going to be a negative number because you have to go back in time to before the body was found. So if you end up getting like, let's pretend we get something easy like T equal to, I don't know, negative 8.25, that means the person died 8¼ hours before it was found. So take your 1:30 p.m., go back in time 8 hours and 15 minutes to what? 3:15 a.m. in the morning. A.m. in the morning, yeah, a.m. in the morning. So 1:30 p.m. back 8 hours, 15 minutes gets us to 3:15 a.m. I will point out I am totally making up this number, right? You actually have to find the number by setting this equal to 37 and solving for T. But that's the idea for this kind of problem. All right, I should definitely stop talking. It's 11:54.